Oh hi! In this video I would like to show you how you can calculate the decay rate of a nucleus that falls apart by sending out alpha particles. In other words, the situation that we're going to look at is a situation where you have a nucleus. And as you know, a nucleus consists of a number of protons, we call that number Z, a number of neutrons, we call that number capital N. And this nucleus falls apart by sending out a very specific combination of protons and neutrons, namely the combination of two protons, Z is 2, and two neutrons, N is 2. This is alpha radiation, this is an alpha decay. This particle, this combination of two protons and two neutrons, is called an alpha particle. And for reasons that come directly from quantum mechanics, this particular combination of protons and neutrons happens to be ridiculously stable. Two protons, two neutrons is an extremely stable particle. In other words, it's very difficult to peel apart an alpha particle to get one of the protons and the neutrons out. So naturally, at the moment that this big nucleus decides to send out a particle, this is the particle it will go for, because this combination itself won't fall apart that easily. Now again, I'm not going to explain why an alpha particle is itself very stable, but just to give somewhat of an idea. Just as in atomic physics you can calculate that there are orbits and you can put a number of electrons in each orbit, and if you fill up each of these orbits with the exact amount of electrons that you can maximally put in there, then that atom is extremely stable. It's called an inert gas. In the very much the same way, you can take a nucleus and calculate what the orbits, they're called shells in this context, what the shells are in the nucleus, how many protons and neutrons you can put in each shell, and if you would maximally fill up each of these shells with protons and neutrons, then that nucleus is extremely stable. If you do that calculation, you will find a sequence of numbers, 2, 8, 20, and so on, and this particular sequence of numbers are the amount of protons and neutrons you can put in each successive shell in such a way that it becomes extremely stable. These are called the magic numbers. And as you can see, the first of these magic numbers is the number 2. So if you would put 2 protons in a particular shell, you would get an extremely stable nucleus. And that's exactly what you have in an alpha particle, because there's 2 protons. So it's called a magic nucleus, because it obeys one of the magic numbers. In very much the same way, you can also put 2 neutrons in there, because that also obeys this sequence of magic numbers. So if Z equals 2 is already a magic nucleus, very stable, then making sure that the neutrons also obey one of the magic numbers makes it even more stable. Now, this one has exactly that. 2 protons, magic number, 2 neutrons, also magic number, so it's called a double magic nucleus, and therefore it's extremely stable. So this is why, if a nucleus decides to send out a combination of protons and neutrons, this is the one it will probably go for, the alpha particle. Okay, so there's that. What we're going to do now is try to find a measure of how often this happens. What is the probability per unit time that this big nucleus sends out one of these particles? Now, in order to do so, we have to look a little bit at quantum mechanics, and we have to look a little bit at classical mechanics, because this scheme that we're going to do now is a combination of these two. So in practice, it won't give you the exact numbers, but it will certainly give you the right order of magnitude. And this is what we're going to look at. Now, the idea is as follows. If you have this nucleus and it wants to send out one of these particles, then what we're going to have to look at is how difficult is it for this particle to fall out of the nucleus. And then you have to imagine that there's 2 factors trying to get these things to stay together, and there's a factor that tries to push that thing out. Now, the thing that tries to keep everything together is, of course, a strong nuclear force, because that is a force that tries to get protons and neutrons to stick together. But there's also a force that tries to push them apart, which, of course, the Coulomb interaction. There's electromagnetic forces that says that this has a number of protons, this has a number of protons, so they're both electrically charged, plus charge, so they try to push each other apart. And that means that you can make this graph of how much potential energy this alpha particle feels when it's within the nucleus. And that's exactly the graph that you see here. This part is a potential well. That's another way of saying this is the strong nuclear force. This is a well. It's a big steep well, and if a alpha particle within the nucleus has this amount of energy, let's call it E alpha, it cannot climb out. It's very difficult for the thing to climb out because it needs at least this amount of energy. That's what the strong nuclear force does for you. Because of the steepness of the well, it's difficult for this particle to fly out. It's another way of saying the strong nuclear force is trying to keep this particle within the big nucleus. But again, there's also the Coulomb interaction, the electromagnetic force that tries to push it out. And the electromagnetic interaction has this hyperbolic shape like this. And the nice thing about the strong nuclear force is that it is very strong, the well is very, very deep, but it has only limited range, which is this range. At some point, the strong nuclear force will lose its strength, and at that moment, the Coulomb interaction, which is this part of the graph, is free to take over. So in this graph here, we see exactly the two contributions to the forces that try to keep everything apart, try to push everything apart to keep everything together. Now, of course, if this were classical physics, then an alpha particle, this combination here, that has this amount of energy, has no chances of finding itself outside of the nucleus, because there is a potential barrier here. It just cannot climb out. So in classical physics, this alpha particle will be trapped within the nucleus for all eternity. But of course, this is not classical physics, it's quantum physics. And in quantum physics, there is a finite probability that a particle that doesn't have enough energy will get to the other side of the barrier, will end up here. Now, it's an exercise in quantum physics to find out what the expression is. We're going to need that expression. So let me just write down what it is. So here's a result just from quantum mechanics. If you want to know how to derive that, you will have to look in your quantum mechanics text. But here's the idea. Suppose that you have, again, a graph of energy. Here's energy. Here's a potential barrier that has a value of phi0. It's a height phi0. And you have a wave function with this amount of energy. That's called E. Now, again, classically, there's no way for this particle, or the wave function represented by this particle, to fly out of the potential because it doesn't have enough energy. It doesn't have enough energy to overcome the barrier. Quantum physics says, well, it is possible. It's called the tunnel effect. There is a possibility for the thing to fly out. And the probability of this happening is called the transmission coefficient. The probability of this particle to fly through the barrier even though it doesn't have enough energy is given by the following expression. Again, this is an exercise in classical physics to find why the expression is as it is, but we're going to just use it as a given. It's this expression right there. The probability that this particle that started out here will find itself at the other side of the barrier. Here's the probability. It depends on a number of things. From just classical considerations, you can already imagine what the things are. First of all, it depends on the width of the barrier. The more wide it is, the more difficult it is. You can see it here. The width of the barrier is called A. There's a exponential in here that goes down as when you make the number A, the width of the barrier, very big. So that sort of agrees with what we would expect, that if you have a wide barrier, the probability of the particle finding itself at the other side is going to go down. It also depends on the height, how high the barrier is. I call that phi0. In fact, if you want to be more technical about it, it's going to depend on how much this energy difference is between the energy of the particle and the energy that it needs, phi0, to get out of the barrier. Now, that is all encapsulated within these factors k and kappa. The factor k is just a measure of the energy that the particle has. So this is this amount of energy with which it enters the barrier over here. That's this number k. So k is just a measure of that energy. And as I said, you also expect this to depend on the energy difference between the barrier and the energy of the particle. That's given by this kappa. It's almost the same expression. It's 2m over h bar squared, phi0 minus e. So if you have a potential barrier of width a and height phi0 and your particle comes flying in with an energy e, then this expression will tell you what the probability is that that particle will find itself at the other side of the barrier. And again, you can see if the barrier is very wide, the probability becomes low. If the energy difference, by the way, this one here, is very small, so it takes only a small amount of energy to climb over, then you can see that kappa becomes a small number, and if kappa becomes a small number, the denominator becomes small and the outcome will become big again. In other words, if the energy difference is not too big, then the particle finds itself with a high probability that it will come at the other side. Again, this is just a result that we're going to borrow from quantum mechanics. It's not difficult to derive this, but this is what we're going to use. Now back to our original situation, where this alpha particle tries to climb out of the nucleus. In other words, it has this energy and has to go to the other side of the barrier here. Now we can just use this expression right there. So here's the probability that the alpha particle will go through the barrier, will find itself outside of the nucleus. In other words, that the nucleus has fallen apart and has sent out an alpha particle. We'll go through barrier. We're just going to borrow this expression. This one right there. It's exactly that. But in order to use that expression, we're going to need two numbers. The two numbers that I just introduced. Namely, we're going to need what the width is, the width A of this barrier. And what we're going to need is how high the barrier is. So let's see if we can find expressions for those. Right? Needed are the width and the height, phi0. Now in our quantum mechanical easier problem, the height of the barrier is very easy. It's just a given number phi0. But as you can see here, the height of the barrier at this point is a very different number than at this point. The height of the barrier differs from point to point because it goes down. The same thing with the width. If the particle were to fly in with this energy, then the width is only this amount. But if it flies in with this energy, then the width is that amount. So what the value for A and phi0 are not given numbers because they differ from the amount of energy. So we have to find an expression for A and for phi0 depending on the energy with which the alpha particle bounces against the side of the nucleus. Well, fortunately, it's not that difficult because this part of the potential is just given by Coulomb interaction. And for Coulomb's interaction, the graph is given by the following formula. Is the charge of one particle times the charge of the other particle divided by this number and divided by their mutual distance. Okay? In our particular case, the charge of the one particle is of course exactly the charge of the alpha particle, which is 2. There's 2 protons. It would be 2e, 2 times the natural charge unit. And then there's q. That's the charge of the other particle. Now the other particle is of course the rest of the nucleus, the part of the nucleus that tries to keep the alpha particle inside. Now if the original nucleus had z protons, then everything except for the alpha particle will have z minus 2 protons. In other words, the charge of the rest of the nucleus is z minus 2 times the electrical charge, unit charge, divided by their mutual separation r. So really what it says here is just what the shape is of this thing as a function of their mutual distance r. And we needed 2 numbers. The height of the barrier at the moment that the alpha particle bounced against the side of the nucleus. Right? That will be the phi0 in our expression here. Well, let's work on that one for a while. It's actually not that difficult because you can already see what the height of the barrier is. It's really just this function, that one, this one, evaluated at their mutual distance. So it's really just that expression over there, 2 z minus 2 e squared divided by 4 pi epsilon 0 r, where r is this distance between them. Let's call it r0. The distance between that one and that one at the moment that the alpha particle is just about to leave the nucleus. It's called r0. So we almost have the expression for the height of the barrier. It's just that we don't know the value for r0 yet. But that's not that difficult to find. Because, and here's another little side note that I'm going to write here, we know from the semi-empirical mass formula that the amount, there you go, that the amount of particles in total in the nucleus, so A is the Z plus N added together, is proportional to the volume of the nucleus. This makes sense, yes? The more nucleons you put in there, protons and or neutrons, the bigger the volume will become. So you can expect them to be proportional. That's what I'm writing right now. Now the volume, of course, itself is meter to the power 3 in units. Now if you want to have a radius and you assume that the volume goes with the third power of the radius, then you can also tell that r, the distance between particles, or excuse me, the radius of the whole nucleus is going to be proportional to the third power, 1 over the third power, excuse me, of the amount of particles in the nucleus. So that's easy enough. Now this r is not yet that r0. R is the size of the nucleus here. So let's call that r of the parent nucleus. And we know that A in this particular case is, there we go, of the parent nucleus, is going to be Z plus N minus 4. Because the parent nucleus is everything except for the alpha particle that tries to fly out. So we know that this A of the parent is N plus Z minus 4. In other words, we know that the radius of this thing is going to be proportional to this number. So that's this, our parent. In very much the same way, we can calculate what the radius is of the alpha particle. Again, we're going to assume that r goes with the 1/3 power of the amount of protons and neutrons put together, and in this particular case that is also easy because the r of the radius of the alpha particle is then proportional to 4 to the power 1 over 3 because it has 4 nucleons in there. It's just this relation again. So what we now have is an idea of how big the parent nucleus is, how big the alpha particle is. And now at the moment that the alpha particle is about to leave the nucleus, in other words when it's over here, in other words when their distance is r0, then we know exactly what that distance is. Because all from this we know that r0 is going to be this number plus that number. R parent plus R alpha. Why plus? Well, again, at the moment that this thing leaves the daughter nucleus, excuse me, the parent nucleus, the alpha particle would have been here. And you can see that their distance, this one is just the R parent plus the R alpha, this amount of distance. And that's exactly what I'm writing down here. So in other words, we know exactly what R0 is at the moment that the alpha particle just leaves the rest of the nucleus. Is given by this expression, and we know that R parent is N plus Z minus 4 to the power 1/3 plus 4 to the power 1/3, and there you go. So we have an expression now for R0, and as a result we have an expression for the height of the barrier. So that number has now been taken care of. Now for the width of the barrier. And by width we of course mean this distance right there. Because this is, as far as this particle that comes flying in at this energy level, this is how wide the barrier is. So this number is going to be called A. And this is the number that we need. Now to calculate that number, that too isn't too difficult for the following reason. Suppose that we are able to find this. Let's call it R star for lack of a better symbol. This distance. And we just calculated what R0 was. It's right over there. then A will be r star minus r0, and that will be our width of our barrier. That's the number that we're going to need right there. So how are we going to find r star? Well, let me make some space here, some room, and show you how that works. As you can see here, r star is by definition the moment that this line is above the Coulomb line. In other words, r star is by definition the following thing. It is the moment that E alpha is greater or equal than the Coulomb interaction. We already had an expression for the Coulomb interaction. There it is. E squared divided by 4 pi epsilon 0 r. Please note, this is now going to be r star. There you are. And of course, what it says here is the moment that it has left the barrier. So it's here or even beyond. The exact moment that they leave each other, the exact position that the alpha particle has gone through the barrier is going to be r star. It's going to be given by an equality sign over there. And then of course you can just easily write down what r star itself should be. Just reverse the formula. Epsilon 0 E alpha. So there you go. That's the width of the barrier. Oh, excuse me, that's not the width of the barrier. That is this distance. And the width of the barrier, as I said before, is this distance, that one over there, minus r0. So A is r star minus r0. And we already know r star, that's this expression. We also already know r0, just wrote it down before. And all in all, what we get here is r star, that's that expression, 2c minus 2 e squared divided by 4 pi epsilon 0 e alpha minus r0. And r0, I just calculated before, is n plus z minus 4 to the power 1/3 minus 4 to the power 1/3. And now we have the width of the barrier. Now, as you can see, at this moment, we can plug in all the numbers that we need. The only thing that you need in order to find A and V0 is just this amount of energy. It enters at several places. And what you need is the amount of protons Z and the amount of neutrons N that the original nucleus had. If you have those numbers, you can put them into these. You find actual numbers for A and V0. And then you can just plug them into this expression right here. And then you have the probability that this particular alpha particle will have flown out of the barrier given that it started out with that amount of energy. Now, we're almost at the point that we actually have the transition rate, how many of particles will fly out per second. Now, so far everything has been pretty much quantum mechanical. There were some approximations made in a classical way. For instance, we assumed that this alpha particle flew in from this side as if within the nucleus there was already an alpha particle present. That is very classical thinking. Of course, in quantum mechanics you have protons and neutrons, they constantly shift and rearrange each other. So in that sense, the idea that an alpha particle came flying in at this side really is just a classical approximation. So there was already some classical mechanics in there, but the rest has been quantum mechanical. Now, in order to turn this number, the probability that a alpha particle finds itself at the other side of the barrier, in order to turn it into an actual decay rate, we need to take one extra step. Let's erase everything that I'm not going to need anymore. And here's the approximation that I'm going to make. Again, it's very classical. Here's Z and N. Here's the alpha particle that tries to get out. There you go. In order to calculate how often a particle comes flying out per second, I need two ingredients. One of them is, given that an alpha particle finds itself at the boundary of the nucleus, what is the probability of it flying out? That's that number. But I also need, how often does an alpha particle within the nucleus find itself at the border of the nucleus? So what I'm saying here is this. the probability of the alpha particle finding itself flying out of the nucleus divided by how often it happens per second is given by this number. The chances of it flying outside of the nucleus, given that's at the boundary of the nucleus, times how often it is near the boundary of the nucleus. How often per second alpha is at boundary. This expression then tells us what the probability per unit time is that an alpha particle comes flying out. Two factors. Now this one we already calculated, it's right over there. Now this part. How often per second is an alpha at its boundary? Here's some classical physics. Suppose that the nucleus has a radius r. We already know what r is. It was this expression that he wrote down before. That's n plus z minus 4 to the power 1/3. There you go. If this were an actual alpha particle flying from one side to the other, then what you will have is that it will take the alpha particle an amount of time delta t 2 times r divided by its velocity to find itself flying from one side to the other side. This is the amount of time that it takes the alpha particle to start here and find itself over there, to cross the whole nucleus. It's just the amount of distance that it has to travel, 2 times this number r, divided by the velocity with which it flies. In other words, the amount of time, or how often it finds itself per second at the boundary, is just this number reciprocated. So 1 over delta t, in other words v alpha, this number just reciprocated, is exactly how often per second this alpha particle finds itself near one of the boundaries of the nucleus. And that's the number that we're looking for right here. Again, this is very classical because we're assuming first of all that the alpha particle is already a particle in itself flying within the nucleus. That's classical. And the second classical part of this is that we just assume that it actually flies around with a constant velocity, which of course we know from quantum mechanics that it doesn't, but it's a good approximation. But then we're already done. Because this number, this is just what we're going to have to plug into there. Now of course the only question is, what is the velocity with which the alpha particle flies from one side to the other, the v alpha? In fact, in principle in quantum mechanics, there is no real way of calculating that, but classically there is. Because we already said that the alpha particle has an energy E alpha. And if you know what the energy of a classical particle is, its kinetic energy, you can turn it into a velocity. Because you know, classically speaking, that the kinetic energy of a particle, assuming also that it doesn't move too fast, so you don't have to take into account special relativity, is given by 1/2 times the mass of the particle times the velocity squared. In other words, velocity squared you can very easily write as 2em, there you go, square root. This velocity of the alpha particle is just given now by its energy with the square root, because of the classical formula, divided by 2 times r, and there you go. So all in all, we can collect all the pieces now. The probability per unit time that a alpha particle finds itself flying out of the nucleus is given by how big the probability is that when it's already at the boundary of the nucleus to fly out, that's this number, in other words that number, times how often it finds itself at the boundary, and from classical principles you would expect that expression. So we're going to take everything together now. The probability per unit time is this big expression, 16k squared, kappa squared, another square, there you go, times 2e alpha m square root 2r. And that's our final expression. This one right here. Now this gives you a pretty good order of magnitude estimation of how often you expect particles to come flying out of the nucleus if it's alpha radiation. And let's, for a recap, just look at what we actually have to put in as far as numbers are concerned. We have to put in the energy of the alpha particle, because it enters on many places. It enters over here, but it also enters in K and kappa, if you remember the expressions from before. So we need the energy of the alpha particle. That's what you have to put in to actually turn this into a number. And what we're going to need is the height of the barrier, in other words, phi0, and the width of the barrier, because they enter over here and in the kappa somewhere. But those are given by this expression, and as you can see, that only depends itself, again, on the alpha, the energy of the alpha particle, and on the amount of protons and neutrons that were already in the original nucleus. So all in all, if you know with what energy the alpha particle is within the nucleus, and you know how many protons and neutrons the nucleus has, then you have all the numbers to fill in this formula, and it will give you an estimation of how many particles per second you expect to come flying out of the nucleus. And it gives you an idea of the decay rate. Now, if you actually plug in the numbers for a given situation, you will find that it regularly fits. In other words, the order of magnitude is usually correct. And you will also find that the order of magnitude is, can have an enormous range. It could be seconds, milliseconds, could also be millions of years. This formula, because of this exponential factor, as you know, exponents go down very rapidly, so there is an enormous range in what this actual outcome will be, just because of this part. Which is true. If you do the measurements, you will find that there's alpha radiating nuclei that only take milliseconds to decay, but you also have alpha radiating nuclei that takes millions of years to decay. And again, it's because of this factor. You do the calculation and you will find that the order of magnitude is usually very correct. There's a final comment. You might wonder, how do you get the energy of the alpha particle to begin with? Because that was one of the numbers you have to plug into here. That's a good question. Fortunately, we can also make a very good estimation of that number, because if you have the situation where you have this nucleus and what comes flying out as alpha particle, you can just by counting the number of protons and neutrons, you can calculate how much mass there was in the original situation. And after the decay has happened, you look at the daughter nucleus, the nucleus that still remains, so Z minus 2, N minus 2, that leftover nucleus, can calculate how much mass that thing has, plus how much mass the alpha particle has, and subtract these two numbers from each other. You subtract these two numbers, you see you have the mass difference between your original situation of one nucleus and your end situation of a daughter nucleus plus the alpha particle, and the mass difference between those two nuclei you can turn into an energy. You will find that some energy has been lost, and by relativity, E equals mc squared, you can turn that difference in energy into, difference in mass into a difference in energy, and that difference in energy will usually be transferred as kinetic energy of the alpha particle that comes flying out. Conservation of energy tells you that the amount of energy should have gone somewhere, and what nature does is put the difference in energy into the kinetic energy of the alpha particle, and that's that number. So even if you don't know this number by heart from the outset or from experiment, you can make a very good estimation just by looking at the mass difference between the original and end situation, turn it into energy. The difference in energy is a good approximation for that number. So you don't actually even need this number, you just need to do the counting of protons and neutrons of the beginning and end situation, turn it to a mass difference, and therefore in an energy difference you have this number. You can do the calculation. I think that's it. Looks beautiful.